Okay, so what I want to do now in the next video or two is I want to prove the fundamental theorem of algebra. Okay, so this is a pretty deep result, but we have all the tools that we need now to prove this. And what I want to do first is I want to state the theorem, and then we'll kind of get into how the proof is going to be structured. So what the theorem says is let P of z be a polynomial of degree d. So what that means is that P of z is a quantity of the form a sub d z to the d plus a sub d minus 1 z to the d minus 1 all the way down to a1z plus a naught. Okay, where we need a few things here. We want d to be at least 1. We need a sub d to be non-zero. Otherwise, it's not a polynomial of degree d. It's a polynomial of a smaller degree. And where these values a sub I, these are complex numbers. So each a sub I is going to be in the complex plane for values from 0 to d. Okay, so P of z, is a polynomial of degree d with complex coefficients. Then there exists a value, let's call it actually, there exists a value R1 so that P of R1 equals 0. And it turns out that that's all you need, is to show that every polynomial with complex coefficients has at least one root. That's enough to give you the fundamental theorem of algebra, because from there, what you can do is you can show, so from here, you know that P of z is going to be equal to z minus r times some other polynomial, P1 of z. Okay, and then what you could do is you could apply the theorem again to P1. Now this is a polynomial of degree, sorry, this should say R1. So this is a polynomial P1 of degree d minus 1. And so that tells you that there's got to be at least one root to this polynomial, and then you can factor that out. And so in particular, what this tells you is that P of z is equal to, if you just apply this again and again, so formally you would do this by induction, but just apply it again and again, and in particular, P of z is going to be the quantity a sub d times the product of all of its roots, z minus r1 times z minus r2, all the way down to z minus rd, where r1 to rd are the dth roots. So they're the d solutions to P of z equals 0. So they're the d, I can't spell. Okay, d roots to P of z. Okay, so every polynomial of degree d has exactly d roots. That's what the fundamental theorem of algebra says. That follows just from the simple fact that every polynomial of degree d has at least one root, because then you can repeatedly factor and then everything kind of follows from there. So that's the fundamental theorem. The reason why we word it like this is that we just want to show that there's at least one root. Okay, that's enough. It turns out that everything follows nicely from that. So that makes it very clear what we need to do. And the first step that we're going to take, okay, so in our proof, we need a few things here. Okay, so the first step, which I'll call lemma 1, is that if P of z is a polynomial of degree d, okay, so just like above, and again, a sub d is not equal to 0, then there exists a value r. So there exists a real number r, so that P of z is bounded if the modulus of z is greater than or equal to r. So that here what I want to say is that P of z is bounded. It's bounded below by twice the modulus of the first coefficient times z to the d. and it's greater than 1/2 that same quantity, if the modulus of z is greater than or equal to r. Okay, and so that's the first thing that we're going to need. The second thing that we're going to need, so lemma 2, is going to say that if p of z is this polynomial, plus a1z plus a naught, and p of z is not equal to 0, then p of z and 1 over p of z, actually we only need it for 1 over p of z, is an entire function. Okay, so it's, I'm sorry, is, what I want to say is that if p is a polynomial of degree d, and if p of z is not equal to 0, then 1 over p of z is bounded. Kind of gave away where we're going to go with this, okay, but that's okay. And then if we have boundedness, the way that the proof follows from these two claims is now really easy, because now the proof follows that since 1 over p of z is entire, because we know that rational functions are differentiable whenever their denominator is not 0. So if the denominator is not 0, then everything's fine. Let me write that a little better. Let's assume for a contradiction. So let's assume for a contradiction that p of z is not equal to 0 for all values z. In particular, that tells you that 1 over p of z is entire. And since 1 over p of z is also bounded by lemma 2, then 1 over p of z is constant, because the only functions that are bounded and entire are the constant functions. And so p of z is constant. Right? If the reciprocal is constant, then so is the original function p. Okay, and again, this just slightly bothers me. I've already written proof, but I wanted to see how the fundamental theorem of algebra follows from the previous two lemmas. Okay, so what we need to do is we need to go back and we need to fill in the proofs of the two lemmas. Okay, so this is what remains, and once we have these proofs, then we're done. Okay, our proof is there. Okay, so again, here's our roadmap. Okay, so this is how the fundamental theorem of algebra follows from the two lemmas. So now we just need to prove the two lemmas. So now let's prove lemma 1, which says that if a function is, if a polynomial, so p of z here is a polynomial, this polynomial is going to be bounded by the modulus of z to the d times some constants if z is big enough. So if we're sufficiently far from the origin. So again, p of z is this polynomial where all the usual quantities, all the usual characteristics, I mean, a sub d is non-zero, d is at least 1, blah, blah, blah. And then we want to show that p of z is bounded in a certain sense. So what I'm going to do is just notice that p of z over z to the d is equal to a sub d plus a sub d minus 1. Think about what's going to happen here. Maybe I should write another term. This is a d minus 1, z to the d minus 1. So if we divide by z to the d, we're going to have a sub d minus 1 over z plus a sub 1 over z to the d minus 1 and a sub 0 over z to the d. Okay, so that's what this quantity p of z over z to the d is equal to. And in particular, what this tells us is that the limit as z approaches infinity of p of z over z to the d is going to be a sub d, because each of these quantities with a fraction with the power of z in the denominator is going to go to 0. So p of z over z to the d is going to just approach this first constant, or actually one slight variation that's even a little bit nicer, a little bit neater, is that p of z, so this is totally equivalent to what I'm saying, but just divide both sides by a sub d, and this limit is going to be 1. Okay. So p of z over its first term is going to go to 1. This is a fact from Calc 1 that we probably know, that you can asymptotically a polynomial is going to behave like its leading coefficient or its leading term. So the limit of p of z over a to the d, z to the d, a sub d, z to the d is 1. And therefore, there exists a value r. So just think about by definition what this means. So there exists a value r so that p of z over a sub d, z to the d is less than or equal to 2 and greater than or equal to a half if the modulus of z is greater than or equal to r. So again, to say that this limit is 1 means that if the modulus of z is big enough, this quantity gets arbitrarily close to 1. And in particular, it's always going to be between 1/2 and 2. Okay, so just that follows immediately by the definition. And then once you kind of unfold this, this immediately gives lemma 1. Okay, so lemma 1 was, if you remember, that 1/2 times the modulus of a sub d times the modulus of z to the d is less than or equal to p of z. And then we have a similar upper bound, okay, just with 2 instead of 1/2. And again, that follows if the modulus of z is large enough. Okay, so that's lemma 1. Now, lemma 2 says that, well, if p of z is not equal to 0, then 1 over p of z is bounded. Okay, and we're going to kind of break this up into 2 parts. So if p of z is not equal to 0, actually we don't even need this hypothesis for what I'm going to say now. But it turns out that no matter what value p of z is going to be bounded. 1 over p of z is going to be bounded by the previous lemma. Okay, so this first lemma gives us boundedness when the modulus of z is large. So first, if the modulus of z is greater than or equal to r, where r is the value from the first lemma, then notice that what this tells us is that 1 over the modulus of p of z, so 1 over that, is going to be less than or equal to 2 over the modulus of a sub d over r to the d. Okay, and so this is going to be, this kind of gives us a nice condition for boundedness if the modulus of z is sufficiently large. And then as a follow-up, if the modulus of z is less than or equal to r, since p of z is not equal to 0, then 1 over p of z is continuous. Okay, and it's continuous on the closed disk D. So this is, remember, the closed disk centered at the origin. So this is all the points that are within a distance r from the origin, including the boundary. So if you have a continuous function on a closed disk, it follows that 1 over p of z is bounded. Okay, so what I just said is not too hard to prove, and it's one of the exercises from the book, but I just use the fact that continuous functions, this is true of any continuous function, but continuous functions over closed disks are bounded. Okay, and there's nothing special about being a closed disk. It just needs to be closed. So you need to have all the boundary points. And this is true of any bounded closed set. So in particular for closed disks. Okay, the function is bounded. Okay, and that proves lemma 2. And so this puts everything together. So since our function 1 over p of z was entire, and since it's bounded, that means it must be constant. That violates all of our assumptions. And remember, I just want to go back and I just want to point out, remember the way that we started this proof is that we assumed for a contradiction that it was not equal to 0. And we showed that if we make this assumption, then the function must be constant. To be constant forces this to be a polynomial of degree 0, and that was impossible, right? We assume that d, we assume that d was greater than or equal to 1. Okay, so what this tells us is that our assumption that p of z was not equal to 0 must be wrong, and therefore p of z must be equal to 0 somewhere. It must have at least one root, and then from there everything else follows. Okay, so that's the fundamental theorem of algebra. I've organized it a little bit differently than the book. Okay, so if you have any trouble keeping this kind of straight the way that I did this, go through and look at the proof from the book, but hopefully this is clear enough. And obviously if there's any questions, let me know.